Hi friends, today we'll be seeing about the topic decision trees from Unit 5. So, a decision tree is a flowchart like structure. It is used to make predictions or decisions. It consists of a node that represents a decision or test on attributes, and it also has branches that represents the outcome of these decisions. The leaf nodes of these decision trees represents the final outcome or the prediction. So, it is used to compare inputs. For example, decision trees are used in sorting or searching. The number of comparisons in worst case equals to the height of the decision tree. So, let's see the terminologies involved in decision trees. The root node, it is the topmost node which has the entire data set for this decision tree, and it is the initial node where we make the initial decision. And then we have the decision or internal nodes. It represents the decisions or the tests. That is, for example, if you are required to make a decision, we initialize it with the internal nodes. So each internal node has one or more branches. These branches helps to represent the outcome of a decision. These branches helps to lead from internal nodes to the leaf nodes. So coming to leaf nodes, these represent the final decision or prediction. So it has the final answer to the whole algorithm. So there is no further split at the leaf nodes. Well, speaking about leaf nodes, the deletion of a leaf node is called as the pruning process. So how does decision tree work? The process of creating a decision tree involves 3 steps. That is, first we have to select the best attributes. The selection of best attributes are done by the metrics for splitting, such as the Gini impurity, entropy, information gain. Then, by selecting the best attribute, we have to split the data sets. After splitting the data sets, we once again have to repeat the process 1, that is selecting of the attribute, until we get the final answer. The advantages of decision trees include simplicity, interpretability, versatility, and handling of nonlinear relationships. Well, even though it has these advantages, it also has some of the disadvantages, such as overfitting, instability, and bias towards features with more levels. Well, the applications of decision trees include business decision making, which is used in strategic planning and resource allocation. It is also used in healthcare to assist in diagnosing diseases and suggesting a treatment plan. It also being used in finance that helps in credit scoring and risk assessment. It is also used in marketing, which is used to segment customers and predict customer behavior. So let's see an example to find the greatest of the 3 numbers. So yes, we are being given with 3 numbers, say for example A, B and C. So firstly, we have to compare A and B, whether A is less than B. If it is yes, and if A is less than B, we have to check if A is less than C too. So if A is less than C, we will be representing A as the lowest value. If not, if C is less than A, that is A is not less than C, will represent it as the C as the lowest number. Then going on to the first decision, that is A less than B, if it is not true, then we'll be checking if B is less than C. And yes, if B is less than C, we'll be selecting B as the lowest number, and if not, we'll be selecting C as the lowest number. Now, let's talk about P, NP, NP hard and NP complete problems. So what is P? That is polynomial time. Some problems can be solved using polynomial time, that is linear time, quadratic or cubic time. So these kind of problems can be solved in a really easy manner, and every steps in this algorithm can be predicted, and we know the steps absolutely. So these problems are deterministic in nature. Some of the examples of these problems are basic math, string operations, sorting, shortest path algorithms, linear and binary search algorithms. Next, it is the NP problems, that is non-deterministic polynomial time problems. These problems can be solved in polynomial time, but the only thing is the steps are not deterministic. That is, we don't know each and every steps. Some of these steps are unknown. So some of the examples of these problems are integer factorization and graph isomorphism. The level of hardness for this type of problem is medium. Next, let's see about NP-hard problems. NP-hard problems are solved in non-polynomial time, and these problems are also non-deterministic in nature. That is, we don't know each and every steps of the algorithm. So this is the hardest type of problem, and it can be solved using non-polynomial time. Some of the examples are k-means clustering, traveling salesman, and graph coloring. So lastly, let's see about NP-complete problems. These problems can be solved using polynomial time, but the thing is, they are the combinations of NP-hard and non-deterministic problems. The NP-hard problems that can be solved using polynomial time, that is, we don't know the steps involved in the NP-hard problem, but if we find the solution of NP-hard, these problems will be included in the NP-complete problems. This is one of the hard problem, and it is not harder than the NP-hard problems. Well, in NP-complete, it includes traveling salesman and graph coloring. This shows the Venn diagram of the NP, NP-hard and NP-complete problems. Here we can see that NP problem consists of P problem, and NP-complete problem is the combination of both NP-hard and NP problems. So let's see some of the formal definitions. We say that an algorithm solves a problem in polynomial time if its worst case time efficiency belongs to OPN, where P of n is a polynomial of the problem's input size n. The second definition is a class P is a class of decision problems that can be solved in polynomial time algorithms. This type of problems, that is, this type of class problems, are called as polynomial. The third definition is a non-deterministic algorithm is a two-stage procedure that takes as its input an instance I of a decision problem, and it does the following. It has the non-deterministic guessing stage, where an arbitrary string is generated that can be thought of as a candidate solution for the given instance I. The fourth definition is a class NP is the class of decision problems. This can be solved using non-deterministic polynomial algorithms. This class of problems is called non-deterministic polynomial. Well, let's see about the fifth definition, that is, a decision problem D1 is said to be polynomially reducible to a decision problem D2 if there exists a function T that transforms D1 instances to D2. That is, if there is a decision problem D1 and a decision problem D2, there will be a function T. This function T helps in the transformation of decision problem D1 to D2. In such a manner, we will say that these problems are reducible. The sixth definition is decision problem D is said to be NP complete, that is, if it belongs to class NP and each and every problem in NP is polynomially reducible to D. Thank you.